For your school-based assessment, you will be required to demonstrate the correct techniques in performing a number of chemical operations. Using a spatula, place the solid in a clean, dry test tube or pour the liquid into the test tube. Never heat in a stoppered test tube, and be sure that open test tubes are pointed away from you and others while being heated. Always heat the test tube at a 45 to 60 degree angle with the test tube holder positioned about halfway up the length of the test tube. Heat the solid or liquid gently at first, and then increasingly more intense until no further change is observed. For gentle heating, pass the test tube slowly back and forth through the flame, and for strong heating, place the test tube in the hottest part of the flame, which is just above the deep blue section of unburnt gases. For liquids, add anti-bumping granules or boiling chips before heating, and ensure test tube is not more than 1/3 full. Liquids often boil in an uneven fashion, resulting in the formation of pockets of superheated liquid. Superheating refers to the heating of a liquid to where its temperature rises above its boiling point without the formation of bubbles of gas associated with boiling. This can be dangerous because when bubbles finally do form, they usually erupt violently, releasing the hot gases that push the column of liquid suddenly out of the test tube. This is called bumping and is easily prevented by adding a few anti-bumping granules or boiling chips to the liquid, which provide a rough surface upon which bubbles can form. Boiling chips are small, insoluble stones made of calcium carbonate, silicon carbide, or crushed coal, just to name a few. These stones have pores inside or sharp points outside, which provide a place for bubbles to easily form. Ensure test tube holder does not come in contact with flame, and never cool test tube under a tap. After heating, carefully place the test tube in a test tube rack to cool. The rule of thumb is to add reagents dropwise until in excess, unless specifically instructed otherwise. Do not pour reagents back into bottles once they are dispensed, and place the stoppers of the bottles upside down on the counter and replace immediately after use. Return reagent bottles to designated position on the table or shelf immediately after use. Unless otherwise instructed, amounts are estimated, and in the absence of suggested amounts, small quantities are always used. Reagents are always to be used judiciously. Do not use reagents that are unlabeled. Place the Erlenmeyer flask, also known as conical flask, on a flat surface and insert filter funnel into the mouth of the conical flask. Flute the filter paper and insert into the filter funnel. The filter paper is a white, porous paper that allows liquid to pass through and retains solids. These folds allow less of the paper to be in contact with the surface of the filter funnel, so the liquid drains through more quickly. In addition, fluting increases the amount of surface area available to the liquid compared with other methods of folding. The funnel should be elevated and clamped into position to allow air to displace readily from the flask and allow the filtrate to proceed quickly. Pour the mixture to be filtered slowly down a glass rod into the filter funnel, ensuring that the level of the suspension does not rise above the level of the paper. When most or all of the liquid flows through the filter paper, then more of the mixture to be filtered may be added until the process is complete. The solid that is left on the filter paper in the filter funnel is called the residue, and the liquid that passes through the filter paper and collects in the flask is called the filtrate. Before commencing the test, dampen blue and red strips of litmus paper with distilled water from a wash bottle and place in a clean covered Petri dish. Commence the test and then place the damp strips of blue and red litmus paper over the mouth of the test tube using a clean pair of tongs, ensuring that the litmus paper does not touch the test tube. Ensure that the test tube is at a 45-degree angle when the litmus paper is placed over the top of it. Ensure the strips of litmus paper are in over the mouth of the test tube before the reaction starts to ensure that any escaping gas comes into contact with the litmus paper. If the litmus changes from blue to red, the gas evolved is acidic. If the change is from red to blue, the gas evolved is alkaline. And if the litmus is bleached, that is, it turns white, the gas is a halogen. Obtain a melting point tube or hold one end of a capillary tube in a Bunsen flame until the glass melts and seals the end. Make a small mold of the finely divided solid to be tested and then insert the open end of the capillary tube down into the mound of solid. Make an oil bath as for melting point determination. Place the liquid to be tested in a mini test tube. Place the open end of the capillary tube downwards into the test tube. And securely attach the mini test tube to a thermometer, aligning the bottom of the mini test tube with the bulb of the thermometer. Partially immerse the test tube in the oil bath, ensuring the level of the substance in the test tube is lower than the level of the oil in the oil bath, and that the bulb of the thermometer is totally immersed in the oil, and clamp thermometer in place. Heat the oil bath at a rate of 1 degree Celsius per minute while stirring with a glass rod until a steady continuous stream of bubbles issues from the open end of the capillary tube. Record the temperature at which this occurs. Remove the flame, allowing the oil bath to cool until the bubbling just ceases, and again record the temperature. These two temperatures represent the boiling point range and ideally should be no more than 1 degree Celsius apart. Top of the burette and fill to just below the 0 graduation mark with a hydrochloric acid, ensuring a continuous column of liquid from tip to meniscus. This may be achieved by opening the tap and allowing some of the hydrochloric acid to drain out, and in so doing displace any trapped air. Rinse a 25 cubic centimeters pipette with a little of the sodium carbonate solution, and using a pipette filler, measure 25 cubic centimeter of the 0.05 molar sodium carbonate solution into the pipette and transfer to a 250 cubic centimeter Erlenmeyer flask. Add 2 drops of screened methyl orange indicator solution and make a note of the initial burette reading. Titrate the sodium carbonate solution with the hydrochloric acid by running small amounts of acid out of the burette into the Erlenmeyer flask, shaking after each addition until the indicator changes color from green to gray. Repeat the titration with further 25 cubic centimeter aliquots of the carbonate solution until 2 concordant readings are obtained. If concordant readings are not obtained, readings which agree to within plus or minus 0.1 cubic centimeters or 3 readings which do not show any trend in values up or down will be accepted. For manipulation of the burette, 7 marks will be awarded for keeping the burette vertical during filling and reading, ensuring there is a continuous column of liquid from the tip of the burette, which means no air bubbles. Reading taken at eye level to avoid parallax errors. Correct manipulation of tap during titration. Conditioning of the burette before titration. Initial reading not equal to 0. Removal of the funnel before taking initial reading. For manipulation of the pipette and the pipette filler, 6 marks will be awarded for correct use of the pipette filler, keeping the tip of the pipette well submerged during filling, eyes at the same level as graduation mark to avoid parallax errors, rinsing the pipette with distilled water before using, correct extraction of hanging drops, conditioning of the pipette prior to use. 2 additional marks are awarded for swirling of the Erlenmeyer flask during titration to ensure complete mixing of the titrant and hydrant, washing down the sides of the titration flask during titration and especially near to the end point. 13 marks are awarded for analysis and interpretation. 4. Calculation of the number of moles of sodium carbonate in pipette volume. Writing balanced equation including state symbols for the reaction. Deduction of the mole ratio between sodium carbonate and hydrochloric acid. Calculation of the number. of Y in a clean, dry test tube. Test any gas given off with cobalt chloride paper and red and blue litmus paper. Observation. Colorless condensate forms near the mouth of the test tube that turns blue cobalt chloride paper pink. Inference. Condensate is water and therefore Y most likely is or contains a hydrated salt. Observation. Gas given off turns damp red litmus paper blue and forms dense white fumes with hydrogen chloride gas. Inference. Ammonia gas given off, ammonium ion present. Observation. Yellow-brown residue. Inference. Possibly iron 2, 3, or lead 2. table and conclusion, 1 mark. Complete list of apparatus and materials, 2 marks. 1 non-essential piece missing, 1 mark. Correct tense, that is third person, passive past tense, 2 marks. 2 marks are awarded for grammar. 1 error, 1 mark. 2 or more errors, no marks. Diction, choice of words with regard to correctness and clearness, 1 mark. Tables, neatly constructed with 4 distinct sides, 1 mark. Correct labeling of table with title written in capital or underlined, columns having proper headings, 1 mark. Proper use of results table, particularly not repeating method in observation column and observations in inference column, and aligning as far as possible observations with relevant parts of the method and inferences with observations upon which they are based, 2 marks. Observation. It should be written in such a way, however, that at the end of your plan, I or anyone else should be able to use it to carry out the investigation. Your teacher will start by giving you a scientific problem. A typical problem is given below. Scenario. Marcia had always heard nutritionists on television say that heat from cooking destroys the vitamin C in fresh fruits and fruit juices. Design an experiment to test your own hypothesis as to the effect of heat on the vitamin C content of a named source of vitamin C. The first thing that you have to do is to come up with a hypothesis for the problem that has been given. In very simple terms, a hypothesis is an educated guess. It is a statement that basically states the solution to the problem and draws upon your prior knowledge and experience. It usually states the relationship that exists between the variables as identified in the problem given. It is also very important that your hypothesis be written in such a way that it can be tested. We say that it must be testable. Here is an example of a hypothesis for the problem given. Vitamin C content is decreased by treatment with heat. You will notice that this hypothesis can be tested. You could, if you wanted to, investigate if the vitamin C content of juices decreases as the temperature increases. The next step in planning and designing is to write your aim. This must be related to your hypothesis. Aim: to investigate the effect of heat on the vitamin C content of vitamin C tablets. It is necessary for you now to list all of the apparatus and materials that you will need to test your hypothesis. Apparatus: Bunsen burner, tripod and wire gauze, 3 conical flasks, 2 beakers, funnel, measuring cylinder, 50 cubic centimeter burette, 20 cubic centimeter pipette, retort stand, burette clamp, dropper. Materials: starch, vitamin C solution made from vitamin C tablets, 0.03 molar iodine. conducted. The responding variable was the tighter volume of iodine solution or concentration of vitamin C solution. That you clearly state how the results will be treated. Treatment of results. Calculate the number of moles in the volume of solution A. Calculate the concentration of vitamin C in solution A. Calculate the number of moles in the volume of solution B. Calculate the concentration of vitamin C in solution B. Expected results. The concentration of vitamin C should be lower in solution B than in solution A. If the concentrations for both vitamin C solutions differ in that the concentration of vitamin C in solution B is less than in solution A, then the data collected supports the hypothesis. If the concentrations for both vitamin C solutions are equal, or the vitamin C concentration in solution A is greater than in solution B, then the data collected does not support the hypothesis. Limitations, sources of error, or assumptions. These should be clearly identified and are the factors that could affect the results. Assumption: vitamin C is not affected by shaking. Assumption: starch is an efficient indicator for this experiment. Limitation: iodine solution is a poor standard as its concentration cannot be reliably predicted from the solid weighed out due to its tendency to sublime and its insolubility in water. Note well that a limitation is a source of error which the experimenter may have no control over due to the method chosen and which ultimately affects the reliability of the results obtained. Here is a sample mark scheme for planning and designing. Clearly stated hypothesis that is testable, 2 marks. Aim relevant to the problem, 1 mark. Apparatus and materials listed are appropriate to the method, 1 mark. The steps are written in numbered steps, logically sequenced using standard English and in the present tense, 2 marks. Method chosen should be able to test hypothesis and fulfill aim, 2 marks. Clear treatment of variables, manipulated, controlled, and responding, 3 marks. Expected results. Data to be collected clearly represented. Type of data collected, whether it is qualitative and/or quantitative, should be apparent. If results are to be tabulated, an example of the results table should be presented. If results are to be presented graphically, a sketch of the graph is expected. 2 marks. Clearly stated expected results in qualitative terms which should be reasonable and based on current knowledge, 2 marks. Clearly stated interpretation of predicted results that ideally supports or rejects hypothesis, 2 marks. Limitations, sources of error or assumptions, any 2 scientifically sound examples, 2 marks.